Okay, hi Nidhi. So we are going to talk about electric current in this one. We are not, next time probably we'll talk about matter than materials. So which one was a self-study, right? So I would definitely recommend that you read up on that also, but for next time. But we'll see about that. So for now, we'll talk about electric current today. I know that you said that you're confident, but then we'll just cover over the basic concepts a little bit quickly. Um, and yeah, so we will get started. Right, so let me just put so open the book and then we can get started. Yeah. Okay. So the first thing that your book talks about are these symbols, right? So you should definitely know these symbols, and most of the symbols are important. Like you should know them for sure, but some of them are more important. I am just covering them. So this is a wire, this is a cell. Then you have a battery, which is multiple cells, and similar to a concept of a battery is also a power supply, which is the same thing essentially. But cell is something that we consider as portable, and power supply is something that we can plug into it, right? Like, but then ultimately they both provide power, so it's all good. You have a resistor, your junction. Junction means that the wires are connected, and you can have a non-crossing junction, right? Like where the wires are not even connected, which is this example. A voltmeter, ammeter switch, you're aware about that. And then the ones on the lower half of the page are just like they're good to know for now, but then at some point we'll be encountering them. So definitely read up on them. If you have any doubt, then let me know. Okay, so let's get started with the chapter. So the first topic that we are going to talk about is electric current. So this is what we're going to talk about, right? Electric current. So first of all, current is defined anything that goes from positive to negative. Like that's the definition of current. So if there is something that's flowing opposite, which is a negative charge, because negative charge will flow from negative to positive, right? Because of it will be attracted to the positive. So then the opposite will be the direction of flow will be opposite. If there is something that's flowing from positive to negative, maybe like protons, then the flow of current will be in the direction of the flow of the charges, right? But for electrons, it will be the opposite. Okay. With that under our belt, let's think about what how the current is generated. So what we need to understand is the picture of what happens inside a wire, right? Because these electrons are inside a wire. So the first thing, so this is say a wire. So what happens is say it's a copper wire. So copper wire is in something called a lattice. So means that these copper atoms are arranged in a regular structure, which is like a table-like structure. So you can see in this case, they are arranged in somewhat like a grid shape, right? Now, all of these copper atoms have in the valence shell, in the last shell, they have two extra electrons, right? Those two electrons they give up, right? So they themselves become negatively charged, all of them. Sorry, positively charged because they give up those electrons, so they themselves become positively charged. And the electrons that they give are now free to roam around. So they just form this kind of this overall blanket of things, right? So basically cores that are fixed inside the wire, and then you have these smaller electrons that are given out from those cores leaving a positive charge behind, and then they form this sea of electrons on top, which is just ready to respond to any electric field, right? So because there are what we call free or conduction charges, conduction electrons, right? So they are just lying inside a wire. Now any free electron, if you put a electric field around it, so plus and a minus, so this is coming from the battery, maybe two terminals of the battery, like something like this, then this thing creates a field inside. This is what we call electric field, right? Now this electric field, because these are electrons and they are inside the electric field, they will start to move. So if there's an electron here, like the red electron, right? So all these are red electrons, which are described as the C later. Every electron, because of that electric field, will feel a force. and then it will all start to move, right? So you can imagine that there are these fixed um, heavy cores, and then there is this thing at the end, and then you apply some field, some push, and then all of that upper layer starts to flow. Okay, if you understand that, that's the basic picture of an wire. So if you also see it on this simulation, that when we bring a wire out, we can see that it shows that it is negatively charged, right? Like in this, it shows the negative charge. It does not mean that overall it is negatively charged, overall it is neutral, but what can move are the positive charges. So say I were to connect uh, a battery. So we can see these electrons start to move after we put an electric field. If we remove this electric field, which is, so now there is no electric field across the wire, so they are not moving. So this is the idea, right? Okay. So let's keep moving if that is the case. So the next thing that we're going to talk about, okay. So is this concept called a charge carrier? So we already kind of discussed it a little bit. We said that current, so what we need to first remember is current flows from positive to negative, right? So that is the main idea. Now, if you have a positive and negative, which we did in case of a wire, like one side is positive, other side is negative, then we see that the electrons were going from negative to positive uh, in this direction, in the opposite direction of the current. So current is flowing like this, and electrons are flowing like this. So it is opposite. If you take an electric field and then you throw a proton in it, and how did you get a proton? That's a different question. Maybe from, like, you did something to the nucleus to get the one proton out, and that proton will move in this direction. Sorry, that proton will move in this direction, which is the same direction as the direction of current, right? So this proton will move. Why will it move towards the right? Because it is attracted to the negative charges, right? So it will move towards the negative side. So the same direction, and this was opposite. So one other common example that's used is a third case here, which is that of a electrolyte, where you have a positive charge and then you also have a negatively charged. But in this case, this solution has both negative and positive charges, right? So the question is, first of all, where do these negative positive come from? So an example would be, say you have HCl and water, so it dissociates into H plus and Cl minus, right? Like it just separates out when in liquid. So this is the positive part, this is the negative part, and then you also have a positive part right here, right? So in this case, what happens? So in this case, it looks like there is movement in both. So the negative ones will flow towards this guy, and the positive ones will flow towards this guy. So there is both are present in this case. So so what so what I want to talk about here is, in all these different examples, what is carrying the current are different things. So in this case, electrons are carrying, in this case protons are carrying, in this case there are ions which are positively or negatively charged, and this is always the case. So there will always be something that will be carrying the current, but the current's direction is always defined from positive to negative. Okay, now if this is clear, let's keep going. So in this case, so can you tell me the direction of the current? So you see the negative charges are moving this way, right? So the direction of current will be from positive to negative, right here, right? So from the positive side, and it's going to the negative side, right? Opposite. Okay, awesome. If we get that, let's keep moving. Okay, next thing we are going to talk about a little bit of a theoretical concept. So let's just bear with me for like 5 minutes. Like see what I have to talk about. Okay, so say that there is a wire of charge density, like charge carrier, what we talked about right now, density of n, right? What does that mean? So charge carrier, we know what it is. So say it is a wire, then the charge carrier will be electrons, and then we are talking about their density. So in this uh, space, in this case, what is the density of these? So we see that there are four per roughly this much length, and then again roughly 3 to 4. Now if you see it in this guy, 1 second, yeah. So in this guy, if you see, if we disconnect this wire, then we see that the rough charge carrier density is per this length we have 2 of density, right? Like roughly, like if you take the total length, then like that. So in our case, uh, we have a charge carrier density which is called n, right? So if we have a wire, then there are roughly, now I'm not even drawing the positive course, but you should remember that a wire is always neutral. So these are so there is a density of n of these things. Now we see that they start to move at a velocity v, right? So let's say in time t, it's just enough time for this guy to come out of this end. So all of them will start to move. This one will come out first, and that time this is coming here, this is coming here, this is coming here, right? Eventually this guy comes out from here, and time t is that time to do that. Okay, let's also call this length L, and the area of this, because it will have some area, so the area A, right? So how many electrons have come out? So my question is this. So how many electrons have come out of this outside this? Answer is simple, right? Whatever is inside this area, inside this volume, has come out of the other end. So we can just simply write what that is. So a number of electrons will be equal to whatever the density is uh, into the volume, right? So volume, we can write it uh, as area times the length, and that will be our number of electrons. What was the net charge of electron that went through? Will be number times charge, so E times NaL, right? So, and then we can say, we can then define what is the current. So current in that case will be, all these charge carriers are there. So current is defined as how much charge has come out of one thing per unit time, right? So all of this charge has flown out, and that has come out in say some time, and that we can just divide. So NaL by T, and L by T is nothing but velocity, right? So NaLB. So this is the formula for current, right? So we basically learned two formulas here. One is this guy, which is current should be uh, the charge by time, right? So it's just a flow of charge. So let's go back, and then let's see where we talked about that these charge carriers are moving. So we just say that out of one area in some time, how much charge is passed, you just divide that to get current. And then we tried to find what that looks like in terms of this number density, charge carrier density, and we got the equation of the current as this guy. So if you know the number density, then you can use this formula to calculate the current. Okay. Now, if you understand this, let's keep going. So the next topic that we want to talk about, again, all of this is in the book. I would recommend that you definitely read through that. Okay. So the next thing that we're going to talk about, this concept of drift velocity. Okay. So now, what happens is your book actually. So we said that because of the electric field, in the wire, right? The So electric field always from positive to negative, and then you have electrons, right, in the wire, and these electrons feel a force. So this is one electron, this is one electron, this is one electron. So as soon as it starts to feel the force of the field, it starts to move forward because of the electric field. So it starts to move faster. So our idea would be maybe it starts from here and then just goes on till here. But what is the problem with this? So you can imagine that when it is accelerating, it might bump into this guy and then it go off in this direction and then maybe in this direction, maybe in that direction, maybe it might go back and then it might follow a convoluted view, right? It might not just collide with the other electrons, it might collide with the positive cores also that are there, right? So the collisions can happen because of various things. So as a result, like even though it is trying to move fast, but because the whole room is very crowded, it's only gets to move at a particular slow speed. Okay. So that current, the net current, is called drift current or drift. So because of that, so the initial velocity that it gets is very high, but then the final net velocity after colliding. So what I mean is this, maybe it is going on like this, like in this way, it's going complicated. So here to here it goes in a straight line, then here, then here, then here, right? So every time it encounters something, it undergoes a collision. That is what we said, right? So every one of this line is like when it tries to go straight, and that is very high. But as a result, it only got from this point to this point, right? So we can draw a displacement vector like this, which is the net velocity, so to speak. Like how much did you actually move? So this speed is very slow. So this is called the drift velocity. So this is very slow. Okay. Fine. So this is what so in our last formula, the v that is used here is drift velocity. So that's a small note that we should do. Okay. So what does this drift velocity depend on? We can just see from the formula that we had gotten, right? So v from the last formula, we can rearrange this formula. We can get I by E and A, right? So we say that drift velocity. So if this is constant, then we can say that the velocity will be higher uh, if the area is lower. One second, yeah. If the area is lower, then the velocity will be higher, right? Area is lower downstairs, then this will increase. And then we can also say that if I is higher, then V will also be higher, right? So let's all try to understand what all this is, like through your book. So I'm just talking about from these things from a book. Okay. So so see, it looks like so you double the current, you double the speed, right? So it's just saying that. So let me just illustrate that with an example. So right now things are flowing at a particular speed, right? And there is a certain current that's flowing. I want to increase that current. So maybe I want to put an extra battery that will increase the current. So you see now they are moving faster. So like just to so if we connect it here, then you see that there it's running slower, and if it's here, it's running faster, right? So the idea is how much the current is, more the current, more the speed, right? So this is what we're talking about here. So this is the second point here. Okay. Other thing that your book talks about, which is this first thing. So if there are a set number of carriers and you need to pass them through a particular, like imagine like water. So if you have limited number of water and you have to pass double the water, like the rate of flow of water should be double. So you should move at a double the speed. Okay. Now, if you constrict it at one side, like we have here, if you have to maintain the same rate here, then in this part they have to move twice as fast, right? So we say that if area goes small, then current doubles, which is this guy. And then the final thing, they say that again, if there are lesser number of electrons, which is the number density is less, then for the same current, they need to move again faster because there are less electrons, right? So one of the example that they talk about here is very interesting, that they say ki semiconductors which have a lower n as compared to metals. So you can see that metals have this higher number and this is 10 power 23. So they are saying that electron mean drift velocities are typically a million times greater than those of metals, right? So because they need to basically move faster, right? Okay. Now if this is clear, let's keep moving then. Again, as I said, these are very basic things, like like you don't probably need them, but you need to understand them to do problems, right? Okay, so the next thing that we're going to talk about is voltage. So we are going to talk about voltage, resistance, and then finally power. So the first thing that we need to do was current. That's done. Okay, so let's keep moving, right? So let's see it like this. So your book actually talks about this topic very nicely. I like it. So it talks about the circuit. Okay, let me do this in a separate video. Let me cut this here. See you.